Good morning. We just checked our homework. We're getting ready to do Lives of Stars. It's on page 136 in your science book. Here we go. All right. The chart up there at the top on page 136 shows you what determines how long a star lives, okay? And it shows you our sun, okay, is expected to live to be about 10 billion years old, okay? That's the estimated life of the sun, about 10 billion years.
Longer than that.
Now, if a star has about 75% of the Earth's, of the Earth's sun's size and mass, okay? If you look at that chart, how long do you think it's going to? You think it's going to live longer than the sun, or less time than the sun? Longer? What do you think? What do you think? Anybody?
Longer?
Longer, yeah. It's actually going to, because if you look, that dot up there at the very top, if you look at the one, that shows you the mass of the star, okay? And our sun is right on the one. See how you read that chart? It shows you 10 billion years, and then one, and you come up, and that they put the point there for our sun. Well, you go on up, and something that is 0.75, the size of our sun, is, of course, inside of the one mark, but it's up to on the 15. So it's expected to live about 15 billion years. One that has 3 times the mass of our sun is only expected to live probably less than 1 billion years. Okay? So the bigger it is, the less life it has. Okay? You would think the bigger stars would live longer, wouldn't you? Because they got more fuel and stuff, right? What happens is, think about it, it's kind of like a car, and it explains this in the book here in a few minutes. Think about the car. You got a little car that holds maybe 12 gallons of gas, and it's got a 4-cylinder engine, but it gets 35 miles to a gallon. So that car will go a long ways, okay? You take a big old SUV, it's got a big old V8, and it might hold 20 gallons of gas, but it only gets 7 miles to a gallon. So it doesn't go, it's not going to go as far. It's going to burn out, it's going to burn its fuel up quicker, okay, because it's burning it faster, so it goes. Same thing with the star. The smaller the star, the longer the life. I see you, Caleb. What?
Okay, so, isn't it true how, like, if you have, like, the same amount of gas, but if you go at a high speed for a while, it runs out faster if you were going
Yes, if you've got a 4-cylinder car and you've got 10 gallons of gas and somebody drives 35 miles an hour and somebody drives 105 miles an hour, whoever's driving 105 miles an hour is burning more gas.
Yeah, yes.
Yes, that is a true statement.
How far across is America, like, if you were driving?
I'm gonna have to hurt myself. What does that have to do with anything?
I was just asking, because,
We're way out in space, and you're worried about driving to California. Lord have mercy.
you can be in space.
I think, I don't know the exact mileage. Somewhere between 3,000 and 4,000 miles. I don't know the exact mileage, to be honest with you. All right. Imagine you want to study how people age. You wish you could watch a few people for 50 years, but your project is due next week. So that doesn't give you a whole lot of time to study people, right? So you're probably going to come up with these different groups for them, though. You're going to put them in groups like babies, young adults, and elderly people. And you can observe the actions of all 3 of those age groups, but you can't observe one person from a baby to an elderly person in the time you've got, right? Well, that's kind of the way scientists are with trying to understand how a star ages. They can't watch one star from creation to death. Okay? They don't have billions of years to do that. Okay? So what they do is they watch different stars, and they can determine what stage of life that star is in. That's how they do it. Okay? struggling with my mask this morning for some reason. Okay? All right. The lives of stars. Stars do not last forever. Each star is born, goes through its life cycle, okay, and eventually dies. And it makes a note to tell you they're not actually alive, of course. They do use born, life cycle, and death just as so something that they can you understand it. Okay? So a star is born. How is a star born? We talked about this a little bit yesterday. You got the nebulas, which is large gas clouds out there, and they're kind of like an incubator to stars. Okay? That's where God kind of like, yeah, okay, we're going to let a star happen here and here and here and here. Remember our previous studies, we talked about how a star is born how often?
Every second.
Every second. About every second. There you go. You remember it.
Like,
Yeah.
isn't that true
Okay.
like a baby?
So a star begins their lives as part of the nebula.
Doesn't like a baby,
Yes.
I could just be hearing things, like doesn't like a baby die and is born every second? Like somebody died and
I don't know if it's every second, but it's it wouldn't surprise me. It wouldn't surprise me. Yeah. I mean, it's just a cycle of life, even for humans. Someone is being born right now, and somewhere in the world, someone is passing away. So, yeah. Okay? But a nebula is a large cloud of gas and dust spread out in an immense volume. A star, on the other hand, is made up of large amounts of gas in relatively small volumes. Okay? In the denseness part of the nebula, gravity pulls gas and dust together. A contracted cloud of gas and dust with enough mass to form a star is called a protostar. Proto means earliest in Greek. So a protostar is the earliest stage of a star's life. Okay? A star is born when contracting gas and dust from the nebula becomes so dense and hot that nuclear fusion starts. Okay? If you remember, nuclear fusion is the process in which atoms combine to form heavier atoms. In Earth's sun, for example, hydrogen atoms combine to form helium. And during nuclear fusion, the enormous amount of energies are released. And nuclear fusion has not yet begun, though, in a protostar. Okay? So it is in its early stages right now. Yes, Bryce?
Well, in that video that we watched with that pastor, and he was like stars, wasn't that where we talked about like every star is being born, like every star?
Yeah, that was. Yeah, he's talking about where did we, he was trying to remember where we talked about a star being born every second. And that was way back at the beginning of almost 9 weeks ago now. Yeah, good job. That's good. Nice memory. Okay? All right. So, lifetimes of a star. How long a star lives depends on its mass. Okay? You might think that stars with more mass would last longer than stars with less mass, but the reverse is true. Okay? You can think of stars as being like cars, and that's what we talked about. Okay? The bigger the star, the faster it burns out its energy. So the life of that star is not as long. Okay? Generally, stars that have less mass than the sun uses their fuel slowly, and they may live up to 200 billion years. Medium-sized stars like our sun, life expectancy is somewhere around 10 billion years. And they think that our sun has probably used up 4.6 billion years of its life right now.
Honestly, it's
So-
not like we're gonna be there.
So, yeah, well, that's it. So you don't have to worry about the sun burning out in your lifetime or your
Yeah, we
great-grandchildren's
still have
lifetime, okay?
5.4 billion.
Or your great,
All right.
great.
Yeah, now we're doing the math. How long is it going to be before, how many generations will it be?
I'd say a million generations.
All right. Now, stars have more mass than the sun, have shorter lifetimes, okay? A star that is 15 times as massive as the sun may live only about 10 million years, not 10 billions, but 10 million years. That might seem like a long time, but it's only 1/10 of 1% of the life of our sun. Okay? So, relatively speaking, it's not that long.
Wait, so is it Beetlejuice?
The what?
Beetlejuice? Is
Beetlejuice?
It was dimming this summer. The lights coming from it was dimming, and they actually thought perhaps it was burning out. The thing is, it is so far away that when it burns out, we're still going to get the light from it for years. So if it's dimming, it's probably already gone.
No, it wasn't. Because the light.
Well, they backtracked on it now and go and think they understand why it was dimming. It wasn't actually burning. They don't think it was burning out. Okay. All right. Now the death of stars. When the star begins to run out of fuel, its core shrinks and its outer portion starts to expand. Depending on its mass, the star either becomes a red giant or a supergiant. Okay?
Or a black hole.
Hold on. They don't just become a black hole all of a sudden. Okay? All main sequence stars eventually becomes red giants or supergiants. Okay? And you'll see up here, okay? After a star runs out of fuel, it becomes a white dwarf, a neutron star, or a black hole. But it does go through various steps to get to those stages, okay?
What's a neutron star?
We're going to talk about that in a few minutes.
Oh.
A white dwarf, okay? Low mass stars and medium mass stars, like our sun, takes millions of years to use up their nuclear fuel. As they start to run out of fuel, though, their outer layer expands and they become red giants. Remember, we have talked about when our sun gets ready to burn out, it's going to become a red giant. It will expand and take up Mercury, Venus, and Earth. It's going to grow that much. Okay, it becomes a red giant at that point in time. So none of those three planets are gone. Okay. In fact, everything is probably turned into total chaos as far as the gravitational pull and stuff like that. Okay. White dwarfs. Now this is pretty cool right here. Okay. The blue-white core of the star that is left behind cools and becomes a white dwarf. Okay. The white dwarfs are only about the size of Earth, but they have about as much mass as our sun. Think about the mass that we talked about the sun had in our solar system. And these things are about the size of Earth, but has that much mass. Okay? So, the sun, since a white dwarf has the same mass as the sun, but it's only about 1/1,000,000th of the volume, is 1,000,000 times as dense as the sun. A spoonful of material from a white dwarf would weigh as much as, would have the mass as a large truck.
It would bend the spoon.
Okay? Okay? You wouldn't know because you wouldn't be able to pick it up.
So even if you have this
Okay.
spoon and like it's so tiny.
A white dwarf has no fuel, but they glow faintly from leftover energy. And after billions of years of being a white dwarf, they eventually stop glowing, and then they become what is known as a black dwarf. Okay, they basically at that point in time they have burned out, and the only thing left is the core. Okay,
Does the core ever go away? Or is it just a piece of rock?
there's a piece of metal, rock, whatever floating around up there somewhere.
Okay. That would be awesome if we could bring that to Earth, like, and have it somewhere outside in the solar system, so we could take chunks of it back. And that would like.
Yeah, that would be amazing if we could bring it back. Yes, sir.
Would it? Or so you know how like it grows when it gets to its final stage. So technically, we'll die before. Like the people then will die before
Well,
the
Earth will not be here at that point in time, not as we know it right now.
Yeah, what I'm trying to say is, if it expands, everything will be burned.
Yes,
You know, because it's
yes,
expanded
it will
so much.
engulf Earth and
Wait.
everything, so it won't be there.
Wouldn't some of the gas giants, wouldn't some of the gases, they might explode because
It very well might. It very well could. That's what I said. Once this happens,
chaos?
it would be total chaos in the solar system. Yeah, but no one's going to be around to see that.
But then again, it might be on Mars.
We're not gonna go to
Leo.
All right, supernovas. The life cycle of a high mass star is quite different from the life cycle of a low mass or medium mass star. The high mass stars quickly evolve into a brilliant supergiant, and when a supergiant runs out of fuel, it will explode suddenly, and within hours, start blazing millions of times brighter. And that explosion is called a supernova. Okay, that's where a supernova is when this thing explodes. Just all of a sudden, boom, and it is just a brilliant, brighter than anything than the stars itself. After a supernova, some of the material from the star expands into space. This material may become part of a nebula, and the nebula can then contract to form a new, partly recycled star. And they think, again, this is where the theory, that's where our sun came from. Okay? The Bible tells us where the sun came from. Okay? All right, neutron stars. After the supergiant explosion explodes, some of the material from the star is left behind, and this material may form a neutron star. Now, a neutron star are the remains of a high mass star. They are even smaller and more dense than a white dwarf. Remember how the white dwarf was so dense that a tablespoon of it, material off of it, weighs more than a truck? Okay? A neutron star may contain as much as 3 times the mass of the sun.
So 3 times.
But it's only about 25 kilometers in diameter, which means it's about the size of a small city. But it's got 3 times the mass of her sun. Yes, that's unbelievable.
That's crazy.
Now, in 1967, you had a British guy detected an object in space that appeared to be giving off regular pulses of radio waves. And some of astronomers hypothesized that the pulse might be a signal from extraterrestrial beings that was trying to contact us. Nah, it wasn't. Okay. However, astronomers conclude that the source of the radio waves was really this rapidly spinning neutron star. Okay. And spinning neutron stars are called pulsars, and they're short for pulsating radio source. Here's the deal: these pulsars will spin hundreds of times per second. They will spin hundreds, not 100, hundreds of times per second. Is that not that's incredible. All right, and now we got black holes.
Yeah.
Everybody loves to talk about the black holes because we're all so knowledgeable about them. Because that's the one thing no one really knows that much about. Yes? Oh my goodness, no.
There's also a white hole.
We know that it's a black abyss that sucks everything in around it.
It's a little
I
space.
don't know where it goes.
We don't.
No, it goes out the other end in the white hole.
All right.
No.
The most
That's
massive
not good.
stars, those having more than 40 times the mass of our sun, may become black holes. Okay, and that, of course, when they die. Okay, a black hole is an object with gravity so strong that nothing, not even light, can escape. Okay, so whatever it sucks in
It doesn't go.
is gone. You never see it again. Okay? After a very massive star dies in a supernova explosion, more than 5 times the mass of the sun may be left behind. The gravity of this mass is so strong that the gas is pulled inward, packing the gas into smaller and smaller space. And the gas becomes so densely packed that its intense gravity will not allow even light to escape. The remains of the stars have become a black hole. Okay? No light, radio waves, or any other form of radiation can ever get out of the black hole. So it is not possible to actually detect the black hole directly.
You
Okay?
would have to see
So they
it.
can't actually see it, okay? They can't actually see this black hole. But they can detect black holes indirectly. For example, the gas near the black hole that is being pulled in revolves faster and faster around the black hole as it is being sucked in. Okay? Friction then heats the gas up, and that gives off X-rays, and they can actually pick up the X-rays. And that's how they can tell that there is a black hole in an area. Okay? They can't actually see the black hole. Similarly, if another star is near the black hole, they can calculate the mass of the black hole because it will have an effect on the gravity of that star.
How far away?
Okay.
So like if you're like, say like 100 feet away, like
Oh,
100, say 100.
you'd be sucked in.
Yeah, I mean not like, I meant like how far away like do you think it could separate?
I don't know. I guess it depends on the mass of the black hole as to how strong it is. And of course, the more it sucks in, the stronger it gets.
Yeah, and the mass of the black hole depends on the star. How big
So
the
they do,
star is.
yeah. So they are able to observe it. They can pick up the X-rays, and they have detected they have detected huge black holes that are millions or billions of times the mass of our sun. That doesn't mean it's that much bigger than our sun. It just means the mass of it is that much. Okay, which is kind of scary. Okay. All right, we're going to watch a couple of videos on black holes and neutron stars. Okay.
Why is it